inverses. Let's take a look at a basic equation, say 3x plus 6 equals 0, and we want to solve this. We know that we need to isolate x, and to do that, we need to remove that 6 and that 3 to the other side, and we use inverse operations. Now, when we have plus 6, we know we need to subtract 6. And then when we have this times 3, we know we need to divide by 3. And that gets us our solution of -2. Why is -6 the inverse of plus 6? Or why is dividing by 3 the inverse of multiplying by 3? The answer lies in the fact that when applying an inverse to something, you reveal what's called the identity. Now, the identity changes depending on the operator. But what we know is if I take something, say A, and I'm going to put this little star that stands for some operator, whether it's addition, subtraction, or maybe some function rule, and I apply it with its inverse. So the inverse, I'm going to say A, and I'm going to put a little -1 as the exponent value to indicate inverse. So this is inverse notation. What happens is this equals the identity. Now, the identity for that operator is something that when applied to that A, gets A back. So when I'm talking about addition, what must be applied to this so that it equals A? So when we're talking about addition in this case, so what must I add to A to get A? We should be aware that it is 0. So when I look at that example before, when I had plus 6, its inverse was -6 because it revealed the identity for addition. So we have this addition operator. So the inverse that applies to that +6 was -6. Again, it gives me the identity of 0. Let's look at multiplication. What must I multiply A by to get that thing back? That would be 1. So this is for multiplication. So that means the additive identity was 0. The multiplicative identity is 1. Manipulating this, we know the inverse should reveal the identity. So if I move A to the other side and 0 to the right side, we know that A plus -A will get me the identity. So using this operator of addition, we can see that the inverse to A is -A. Manipulating the multiplication one. If we move 1 to the other side and A back to the left side, we don't want to subtract it over, but if we divide by A, dividing by A is the same thing as multiplying by the reciprocal of A. We'll see that this, again, where our operator is multiplication, the reciprocal represents the inverse, because again, these represent our identities for this specific operator. So what must I apply to A to get the identity? -A and 1 over A. So what we want to take away from this is the inverse is going to be what reveals the identity. So when it comes to functions, we want to know what must I apply to f of x, or we know the operator with the inverse of f should equal the identity. Well, what's the identity for a function? What's the identity function? We're looking for a function that when applied gives me that thing back. That function is y equals x, right? With addition, when I applied 0, I got that thing back. When I applied 1, multiplication, I got that thing back. With a function, when I plug in x, I get that value back. So this is called the identity function for that reason. Now, knowing that I want it to equal x, again, this doesn't stand for multiplication, but it's some operation that we are not familiar with yet. That requires what is called function composition to identify an inverse. But we're going to save that for a later time. So what we're going to look at now is how do we identify an inverse function visually, and let's use that to find inverse functions algebraically at the end. because we know that y equals x is our identity function, when we're working graphically, to identify an inverse, it is going to be visually a reflection about the line y equals x. So if I plot this graph, y equals x is just linear, slope 1, y-intercept of 0. If I take some function and I reflect it over this line, that will be a visual representation of its inverse. But instead of taking whole functions, let's just start with a coordinate. So if I look at a coordinate, say 1, 2. So I go over 1, up 2, and I plot that. And I want to reflect it over this line, y equals x. A reflection requires that the final location is equidistant from the line of reflection as when it started. So something that would be equidistant would be at the point, say, 2, 1. So if I started with 1, 2, and then its inverse location was 2, 1, we can conclude that for some coordinate, to get the inverse location would be to just swap the x and y coordinate values. And you'll notice with other examples, if you try this, you will verify that fact. So with a coordinate, we're going to swap the values for the inverse. And visually, by a reflection over the line y equals x. And the reason we started the video with that talk about identities is because I want you to realize why it's a reflection over y equals x as opposed to something else. This y equals x, we said, is the identity function. And one final time, the reason it's called the identity function is because when I plug in something for the input, I get that same thing as the output. So that is why we reflect over y equals x and not some other line. So now to see how this is put into use, let's take a look at an example of a table of values that represents some relation. So this isn't necessarily a function, but it'll lead us into the function. So let's say we have the following table. Now I'm actually going to take this over to Desmos just for a better visual. But let's just look at a single coordinate first. So first let's get that line of reflection in there. So y equals x. And let's put in a coordinate, say our point 1, 2. If we zoom in, we'll see that our point, in terms of its distance from this line, vertically 1 unit above, horizontally 1 unit over. Okay, we can get there. But let's input some other point by swapping the coordinate. We'll see vertically 1 away that way. So we have equidistant point, and you can see it looks like a reflection over that line. But that's just a single point. Let's say we want to add in a table. So if we do plus, we'll add in our table of values. We're going to do 3, -1, 4, -2, 1, -4, and -1, -4. So we have these points plotted. We'll zoom out a little bit here. And if we want, we can connect these points. If I just hold down this here, we'll check off lines. So we get everything connected. Now we know if we want the inverse table, we can add another table. And we just discussed to find the inverse location of these points, we're just going to swap the x and y coordinates. So it's going to become -1, 3, -2, 4, -4, 1, and -4, -1. And if we connect these points, we should see that we have identified a inverse location for each point, and visually this looks like a reflection over the line y equals x, that identity function. So now, if say we were to identify the domain and range of this relation, the domain of the green relation, we can see it spans from -1 on the x-axis all the way over to 4. So its domain is -1 to 4 inclusive, right? Both -1 and 4 are included in the set. Its range goes from -4 up to -1. So let's keep that in mind when now analyzing the domain and range of this. The domain goes from -4 to -1, and the range goes from -1 to 4. That was the exact opposite of the domain and range of the green relation. And that should make sense because in order to find the inverse locations, we swap the x and y coordinates. And if x corresponds to domain, the inputs, and y corresponds to range, the outputs for our relation, however these points are related, it should make sense that the domain and range of one becomes the range and domain of the other, because we swap the x and y values which correspond to domain and range. So that is how we handle a relation or a set of points. But now let's say we want to talk about an actual function. For this video, we're going to stick with linear functions because as the functions change in, or they become more complex, things that we have to consider are added to this process. But to find inverse functions, the process is as follows. We have some function. The first thing we want to do, so it equals something. Actually, I don't want to use y for the sake of this. Let's actually do just a straight up linear equation. We'll do 2x minus, say, 1/2. So again, we're going to stick with linear equations, but this process that we'll write off to the side is true for all types of functions when trying to identify the inverse function. The first thing I want you to do is rewrite as y equals if that is not already the case. So instead of f of x, we're going to use y. And the reason for that is because of the next step. We know with coordinates, we swap the x and y coordinate to find its inverse location. We're going to do that same thing with a function. We're going to replace the x's with y's and the y's with x's, serving as a swap. So replace x with y and y with x. So x equals 2y minus 1/2. Now we're asked to find the inverse function of y, so we want our independent and dependent variables to stay the same. When we started, this was y as a function of x, so my final result, we want it to be y as a function of x as well. As it's currently formatted, this is x as a function of y. So independent variable, and when we started, was x, and dependent was y, because y depended on the value of x. But this equation here, the independent variable is now y, and the dependent is x. So we want to change that to stay consistent with the original function. So all we have to do is just resolve for y. Resolving for y, we'll add 1/2, and then divide by 2 to get y equals x plus 1/2 all over 2. Now, because we have a fraction within a fraction, let's clean this thing up. Dividing by anything is the same thing as multiplying by a reciprocal. So let's write this instead as x plus 1/2 times 1/2. The reciprocal of 2 is 1/2. Distribution, we'll get 1/2 x plus 1/4. Now, the very last thing we want to do is make sure we use inverse notation to indicate that that final result is actually an inverse. So our original function is defined as y. We don't want to define this as y as well. So all we have to do is tack on a little -1 exponent as our inverse notation, or if you want to convert it back to function notation, you would write it like this. So here is our original function, and here is its inverse. And we have the step-by-step process off to the side, and we can check our answer by seeing that we have a reflection over the line y equals x if we were to graph these two linear functions. So step one, write as y equals, swap the x and y's. Now, if there's more than one x in the equation, you have to replace all the x's with y's and all the y's with x's. That's why we want to format the algorithm like this as opposed to just swapping. Just so you're careful with multiple x's in a function, you know to replace all of them with y, then resolve for y, and finalize with inverse notation. So just to check our answer, let's jump over to Desmos. We'll leave y equals x in to check as the line of reflection, but we started with y equals 2x minus 1/2. Do a different color here. And then our inverse function that we found was, we can actually call that f of x. G of x equals, and then we found it to be 1/2 x plus 1/4, I believe. And you can see that our line of reflection, we can even make it dotted if we like, but you can see that that black g of x function is in fact a reflection of the red f of x function that we started with. That is a clean reflection over that identity function y equals x. So that is the process on how to find an inverse of a function algebraically, and that is how we will conclude this video, and that's how we'll end our introduction to inverse functions. So there will be more to come on this topic as we increase the difficulty or the complexity of the functions moving forward in the course, but we will start there.